So we are going to continue this lecture, and in the next 30 minutes, we are going to be talking only about one thing only, and nothing but that one thing. We're going to be talking about the cofactor of it. The cofactor of a tensor. We have talked about the inverse of a tensor. We have talked about the transpose of a tensor. We have talked about the deviatory part, the skew part, the symmetric part, the spherical part, the components. But here we are talking about something that has a very, very great physical meaning. And that thing is called the cofactor of a tensor. Unfortunately, textbooks are written from a mathematical point of view, and they do not do sufficient justice to this. I only saw one that seems to give the necessary ingredients to really instructing on what this important aspect of a tensor is about. Therefore, I did some little more work on it, and I hope you will be a beneficiary of that effort if you look at it very well. In continuum mechanics, when I say continuum mechanics, I mean in strength of materials, elasticity, plasticity, fluid mechanics, heat transfer, thermodynamics, all the courses that engineers take that have mechanics on it, they are all branches of continuum mechanics. In continuum mechanics, we are concerned with changes in shape of objects that have been subjected to mechanical, thermal, and inertial loads. So when you load something, that thing is subject to changes in shape. You may not notice the shape. The changes in shape may be so insignificant, they may be so infinitesimal. No matter how small they are not insignificant because they are what leads to the resistance of the object. If you put your back against a wall, you may not know that that wall has moved, but it is the small movement that you cannot perceive in that wall that makes it to react and be able to carry your load. If not, the wall would have collapsed. But because it's able to bend and therefore resist you, that's why you could. And then how much it gives is going to depend on how much it bends. That's why, even though a wall is an inanimate object, that's why the wall will give, if a bird lies on it, it will give you a small reaction. If it's a gorilla that stands on the wall, it will reply the gorilla by giving sufficient reaction. How does it know? Because the gorilla will tend to bend it more than a bird. So therefore, you can see that on a string or a rope. If you put a slight weight cloth on a rope, it won't change. If you put your blanket on it, it will bend more because it needs to bend more to be able to carry the load that is heavier. So what happens is that whenever there is a thermal, a mechanical, or an inertial load on any structure, that structure will change in shape. The shape change may not be noticeable, but it is there. And that is what engineers study to be able to find how to design those things and be able to give them the strengths they need. We shall see later that what really happens is that these external loadings create tensors that spread inside the material. Those tensors can be stress tensors, can be strain tensors, they can be deformation tensors, and there are so many of them. We are interested in what happens to line elements in the material. Let us say you just take an imaginary number of particles that fall on a line. After a mechanical load has been applied, you want to see what happened to the vector that considered that line later on. If the particles are very close together, we're assuming that the line did not bend, it's just changed. So it's like the tensor that is now operating inside the material has transformed that line to another thing. That is what caused the change in shape. So we're interested in what happens to the line element in the material, where such strain, deformation, and all these tensors have been created by external loads. You will see now what part deformations play. What comes, it will be our business to demonstrate, that is in chapter 4 of the book, Kinematics, that small line elements are transformed by applying deformation gradient tensor to the original. vectors of undeformed line elements into the original vectors of the undeformed line element. So if you want to get the final line element, you just apply the deformation gradient tensor to the original vector and you'll get it. The question that arises is that if we know that the deformation gradient, there's a particular tensor that changes the small lines to their new state, what happens about the vector areas? You remember that if you have two vectors, the parallelogram they form constitute an area. If the two vectors change because of transformation, because they have been transformed by a vector, the areas also will change. The question is it that same vector that is responsible for transforming the area? We will show that when a tensor transforms lines, the corresponding vector areas are transformed by the cofactor. It is not the vector that transforms the lines that also transforms the areas. That is the reason that is where the cofactor was born. And I think I have a diagram here. Look at this diagram on the right-hand side. I note here that most textbooks introduce cofactor in the most unappetizing way. Don't mind them. Let us say this is vector V. And this other one is vector U. And the area in white in between them is the parallelogram formed by U and V. And the magnitude of that area is covered by its magnitude and direction by U cross V. Its magnitude is this. If you take the area here, and the direction will be perpendicular to it. This my slide is use up that. There will be a vector perpendicular to it whose magnitude is equal to the area here, and it is given by U plus V. Now, suppose a particular tensor has transformed vector U, the blue vector, to TU. It's no longer at the same, it's now a vector that has changed magnitude and has changed direction. So what was U before is now TU. What was V before is now TV. That is the tensor T operating on V. You know it will give us a vector. So that means that the area we had before is now TU cross TV. The question is, suppose we want to express that area in terms of U and V. What tensor was transforming it? We define that tensor as the cofactor of T. This is the original, this is the definition, this is a triple equality. This is the definition of the cofactor of, because you know that once U has been transformed and V has been transformed, you know that U cross V has also been transformed. What can give, of course, if you can express it as TU cross TV, but suppose you want to express it in terms of U cross V, that tensor that transforms U cross V to its final state as a result of the transformations U and V have received is defined as the cofactor of T. You can see here, we have defined cofactor. No mention is made of inverse. No mention is made of components. This is the most elementary, the foundational definition of a cofactor. It is so fundamental that any other definition of a cofactor you read in any book, in anywhere, you get from anywhere, we can derive that from this statement. Everything can be derived from this statement. So vectors U and V have been transformed by T to TU and TV. How is the vector area TU cross TV created by these two vectors in a transformed state related to the original vector area U cross V of the parallelogram as shown? The tensor transforming the area of the parallelogram sides that have been transformed by T is called the cofactor TC of T. This is the physical meaning of the cofactor. Any other definition can be obtained from this physical definition. So this is the fundamental definition of cofactor. So all we would then be doing, we are now going to, first of all, obtain every other definition of cofactor that we have, and then find its components, find everything we need to find. But this is the crux of the matter. This is where the cofactor is physically defined. If your book, if the book you are reading does not define it this way, bring the definition to class. We will prove that that definition can be derived from there. It doesn't matter how it defines it. Whatever it is, if it defines it correctly, we will get that definition from this definition here. So it's a derived. So this is the fundamental thing. Even the definition we gave last week can be derived from here. But that definition was weak because it requires the tensor be invertible. This one does not care whether the tensor is invertible or not. Just give it any two vectors, u and v, as long as those two vectors are not, they are not collinear. If once they are not collinear, the result will always be correct for the cofactor in terms of any tensor T that transforms U and V. Now, let us find the components of the cofactor. Now, to find the components of the cofactor, I'm using these two relationships. If you have been doing your self-test, this relationship would have been tested over and over. So you should know this relationship. If you don't know this relationship, it means three things. You have not been reading the book, you have not been testing yourself, and you have not been going through the worked examples that you have been given. And that's a very dangerous sign, because that shows that you are not prepared to credit this course. You want to see me again next year. I don't mind seeing you. So if you like me so much that you want to stay with me here and not go and be seeing me every year, if you have people that are sponsoring you to do that, fine. So for a tensor T, the cofactor, let the cofactor TC have these components. So we are now going to find Tij of TC so this is an unknown. So we want to find that unknown in terms of the either the components of T also. So clearly, if these are the cofactors, if these are the components of the cofactor, you remember the component of any tensor is the inner product of the tensor with its dyad basis. And it can be written as ei.tcej. So these are two expressions for the inner product. If that is the case, we use the fact that ei cross ej, is it ei? Is ei cross, what is, let me see what I have here. I want to just check. I'm seeing there's an error of some sort here. There's something that is not clear to me here. Let me just see. Okay, yes. There's no problem there. This next line is coming from the second expression. It's not coming from the first expression. This EI is coming from this second equation here. That is this one. And this EJ is also coming from that expression, that second expression. So it is this expression that gives us this, not the one there. So if you have difficulty with that, please go to the worked examples and see that these are defined and proved. So this and this are coming from this second expression. So once you have done that, you can bring out the alternative tensor EI alpha B and EJMN that are here, bring them out because they are scalars. And then you have E alpha cross E beta, and then you have EM cross EN, and then you have TC here. So on this line, from here to here, we are reminding ourselves that if you have TC transforming EM cross EN, by definition is the same as TEM cross TEN. That is what we have. We're using this expression here, which defines the cofactor. We're using it to write the cofactor in terms of the T. So in the terms of this T. So from here to here, we are using the fundamental definition of the cofactor. So cofactor doesn't appear any longer from here on. And we have here 1, 2, 3, 4 tensors. These 4 tensors are they are pairwise in cross product, and then the results are in dot product with each other. When that happens, go to question 1.15 in your book. You will see that this expression is there. So you have a situation where A cross B dot C cross D, which is here. A cross B dot C cross D. So we have the expression here. So it gives us, we're just using this formula. So that is E alpha dot TEM, E beta dot TEN minus E beta dot TEN, E alpha dot TEN. So that is what you have here coming from this formula. So if you, all you need to do is to interpret what is A, B, C, and D in this expression here. This is A, B, C, and D. If you do that, you'll find that this expression is obvious from this something that was worked out in question 1.15. So if you have difficulty with that, go to question 1.15. Now, the big step here is how to move from this 1/4 E alpha beta EJMN into this to half. This 1/4 becomes half, and it's only the first term that matters. The question I'm asking is this. I want you to go to the chat room. Does this expression mean that E alpha dot TEM and E beta dot TEN is equal to minus this? If it is, then that is double. Then that's why you got this one. Is that what it means? Is this true or false? Is this equal to this negative? Because that is one way you can get this. Is that what it means? Tell me whether it is true or false. This expression. Does it mean this? Is it true or false? Aboluwatife, I think it is equal. Oh, is it? Oh, no, this is from the previous question. 1232, 1232. Oh, yes, Aboluwatife is just answering me. No, it's equal. How many people agree with Aboluwatife? True. Kamal says false. Oluwatomiwa said true. I think it's true. Oluwapelumi. Olatunji, true. James, true. Okay. True. The answer is, it is false. It is false. So this step from here to here is what you should take home and work out. It is when you use this to operate on this that the answer you get in the first one will be equal to negative of what you get in the second one, that they become additive. These two on their own are never equal. But when E alpha beta, and the way to see it is this. You look at what is happening here. You have alpha and N here. This is alpha and N. And then you have beta and N. Beta and N. Alpha and N, beta and N. You see that you have beta and N here, which is a reversal. And alpha and N, alpha and N. And you can see that once you swap, you can have the same indices for all of them, but this expression here will be negative. So because the expression is going to be negative, that is why one negates the other. It's only after applying the alternative symbol that you are going to get that. That is where the negativity actually comes out of. So it is not, it's not coming from the terms themselves. You work this out. Don't assume you know what is happening between this line and this line. It is by the time you apply EI alpha beta EJMN to this one, and you apply to this one, that you are going to get that. The expression you will get at the end of the day will be, one will be the negative of the other. So that's why you just take twice the one expression and you are okay. And at the end of the day, TIJC is equal to half EI alpha beta EJMN T alpha N T beta N. So these are the components of the cofactor in terms of the component of the original tensor. So we can therefore say the cofactor tensor in component form is TC is equal to half EI alpha beta EJMN T alpha N T beta N EI circle times EJ. So that is, so I'm asking here, what is this, what is this E alpha beta? So you will again go to the notes, you'll see that when you have, when you want to find, for instance, the trace, if you want to find the trace of the cofactor, you know you are going to change this to dot. When you change this to dot, that means that this I and J will be the same. So this one will be EI alpha beta and EINN. So you now have to find a way to express this in terms of the deltas, and it is in your notes. You can express this product in terms of the deltas, and when you do that, when you express it in terms of the deltas, we have tried to find the trace, which is the second principal invariant, is the trace of the cofactor. So you now have EI.EJ, which gives you delta IJ, which makes I and J the same. And therefore, once you do that, you have this expression here. And at the end of the day, you are arriving at the same expression we already got from another method, which is saying that the trace of the cofactor is half the square of the trace minus the trace of the square, which is exactly the same expression we obtained from the definition of the second principal invariant. So that expression is the same as what we obtained before. So that's why this is this thing is the trace of the cofactor. Now we have the cofactor properly defined here in terms of its components. Take its trace, you are going to get the second principal invariant. So what do I have next? The next thing we are going to do is to show that the expression, the definition we gave last week, that the cofactor is T transpose inverse or inverse transpose determinant of T. We can now show the equivalency of this to the original definition. We've already taken the fundamental definition and we have used it to find the components. So we can now find the second definition that we gave last week, which is a weaker definition because it is assuming that the tensor has an inverse, whereas the tensor does not have, a tensor does not need to have an inverse before you can get a cofactor. So, but for those that have inverses, you can also define their cofactors like this. But this definition does not apply to tensors that have no inverses. So that is what we are saying here. So this is only applicable to tensors that have inverses. But for those ones, you can see that this is also the same thing that you can derive from the original definition. Now, because this is rigorous, just like what I've just taken you through is rigorous, I want to end the class quickly to give you time to digest what we have done today because it's a heavy dose. And what I want you to do, go home, convince yourself of this step. This is the crucial step here. So don't think you understand this. Open this up. I think the thing is fully worked out in the text. I worked it out in one particular place in the text. So go check the text. Check the text. Check the worked examples. I'm sure this is there. So go look at it and see why this moves on to this. So this is a crucial step here. Every other step is easy. This one is not immediately obvious. So I will be calling it a day here. We would have gotten halfway in our treatment of the cofactor. Next week, we'll complete talking about the cofactor. And then after that, we will now go to orthogonal tensors. And then what else do we do? And then we now talk about the eigenvalue. And we talk about what tensors are orthogonal, what are proper orthogonal, what are not proper orthogonal. And we talk about axial vectors and some other things. So, but I think this is a very, very good place to stop. You can continue from there next week. Please make sure you read through the worked examples you are given. Make sure you go through the solved problems as well as the text. Even though I'm teaching with the slides, the text is a little bit more detailed than the slide. So I should have mentioned everything in the text in my speech, but That will be an easier way for you to remember. And then the 10 marks of the 10 marks that you get for our WOOF marks are coming from two things. They are coming from your class participation and from your attempts at your different self-tests. It is if you attempt them more and then you answer questions, you are going to get a good chunk of those 10 marks. So if you don't do them at all, get 0 in those 10 marks. And then I will not be sympathetic with you if you are on the borderline. If you are in, but these are marks that can help move you on the borderline. But they are marks you earn by participating in class, by asking questions, by answering questions, by chatting, and then by going to your self-test platform and doing the self-test. So those are the things that are important. So I am seeing today now only 20 students are here. I also have a record of all your class attendances. Every class attendance is known. So there are some people who ought not to even be in the final exam because there is a percentage of classes you are supposed to attend to even be able to take the exam. So if you don't want us to use that rule on you, please tell your friends that are fond of absenting themselves that rules can be, because we have documentary evidence, rules can be used to stop you from even participating in the final exam. Because it's still students that are going to complain now at the end that we didn't give them good marks, who are not coming to class now. But for those of you who are regularly attending and participating, you should be aiming to score a very good grade in this course. Well, on that note, at time 12:42, I think it's not a bad time to say, have a nice day and enjoy the rest of your week. Goodbye.